Every single time you send an email, buy something online, or just browse the web, you are relying on this hidden world of super complex mathematics. It's like a silent, invisible war that's being fought every nanosecond to keep your information safe. Today, we're going to pick the locks on that world and see how modern cryptography actually works. So let's pull back that curtain and see how these invisible locks are made.
Okay, so imagine this. You and a friend are in a super crowded room and you need to share a secret. You can't just whisper, right? Because everyone is listening. Well, the internet, that's the crowded room. So the big question is, how do you create a private conversation in a totally public space? This is the fundamental problem that cryptography has been trying to solve for centuries.
So the first and most obvious solution is, hey, let's just agree on a secret code or a key before we start talking. Simple, right? Well, not quite. This leads to a classic chicken and egg situation.
And this right here is the key exchange problem. Think about it. If you and I need the exact same secret key to encrypt and decrypt our messages, we first have to get that key to each other securely. But if we already had a secure way to communicate, we wouldn't need the key in the first place. It's a paradox that stumped experts for decades, until, that is, a brilliant idea in the 1970s just completely flipped the problem on its head.
And the solution was to stop thinking about a single key. Instead, what if you had a system with two keys? This was the birth of public key cryptography, also called asymmetric cryptography, and honestly, it is the foundation of almost all modern internet security.
So here's how this totally solves our problem. Imagine I generate a pair of keys that are mathematically linked. One of them, my private key, I guard with my life. I never, ever share it. But the other one, the public key, I can shout it from the rooftops. I can post it on a billboard. You can use my public key to lock or encrypt a message and send it to me. But here's the magic. Once it's locked with my public key, the only thing in the universe that can unlock it is my matching secret private key.
So what makes this so secure? Well, it's all built on a kind of mathematical one-way street. It's really easy for a computer to take two massive prime numbers and multiply them together. Boom, done. But trying to go backwards, taking that gigantic result and figuring out the two original primes that created it, that is an incredibly difficult task. So hard, in fact, that it would take the fastest supercomputers we have today literally thousands of years to crack.
But of course, no system is perfect. The moment these digital vaults were built, code breakers immediately started looking for ways to crack them open. The battle for digital security, you have to remember, is never static.
And you know what? Attackers found some pretty clever cracks in the armor. They realized they didn't always have to solve that impossible math problem head-on. No. Instead, they could do things like listen for tiny variations in the time it takes a server to decrypt different messages, or even trick a system into revealing tiny clues about the secret key. It's a constant cat-and-mouse game.
And this kicks off a massive, continuous arms race. As our computers get faster and better at factoring, the keys have to get longer and longer and longer just to stay one step ahead. But these gigantic keys, they make everything slower and way more power-hungry. The digital world needed a new kind of lock, one that was just as strong but a lot more efficient.
And that brings us to the next generation of public key cryptography, elliptic curve cryptography, or ECC. It's an elegant, powerful, and much more efficient way to secure our data. Now, at its heart is this equation that looks deceptively simple, but when you plot all the points that solve this equation, you get these beautiful, really complex curves. And it's hiding inside the geometry of these curves that we find a new, even harder mathematical problem to solve. So here's the new hard problem. Imagine you pick a starting point on this curve. Your secret key is just a number, let's say it's 5. So you hop along the curve 5 times to land on an endpoint. Now, calculating that final endpoint is super easy for a computer. But now, flip it. If an attacker only knows your start point and your end point, trying to figure out that you took exactly 5 hops to get there, that is a monstrously difficult problem. It's way harder than factoring large numbers. And here is the brilliant payoff. Just look at the difference on this chart. Because the math underneath is so much harder, ECC can provide the exact same level of security with a much smaller key. To get the same strength as that huge RSA key, you only need this tiny little ECC key. That's a massive difference, and it makes ECC way faster and absolutely perfect for devices with limited power, like all of our smartphones. Okay, so far we've been totally focused on keeping messages secret.
But that's only half the battle. How do you know the message you just received hasn't been tampered with along the way? And maybe more importantly, how do you know it really came from the person you think it did?
This opens up two other really crucial goals of cryptography: integrity and authentication. So, confidentiality, that's all about secrecy. Is it secret? Integrity is about making sure the message hasn't been changed. And authentication is all about proving the sender's identity. So one way to guarantee integrity is with something called a message authentication code, or a MAC. You can think of it just like a tamper-proof seal on a bottle. The sender takes the message and a shared secret key and combines them to create this little tag, the MAC. They send data along with the message. Then the receiver does the exact same calculation on their end. And if their new tag matches the one they received, they know for sure the message hasn't been touched.
A digital signature, though, gives you even stronger proof. Here's how it works. First, you run your message through a special function that creates a unique, fixed-length fingerprint. We call this a hash. Then, you encrypt that hash with your private key. Now, anyone in the world can use your public key to unlock the hash and check it against the message. If it matches, it proves two critical things. One, the message is unaltered, and two, only you, the holder of the private key, could possibly have signed it.
So, we've built some truly incredible locks. But this brings us to one final, absolutely massive challenge. We've got all these public keys flying all over the internet. How on earth do we know that the public key we have for our bank actually belongs to our bank and not some clever imposter trying to trick us?
Yeah, the early ideas were pretty flawed. First, people could just, announce their public keys. But that was way too easy to forge. The next idea was a trusted public directory, kind of like a phone book for keys. But what if an attacker could just hack the phone book itself? We needed a much more robust system for verifying who's who.
This led to the idea of a public key authority. So before Alice talks to Bob, they both check in with this central trusted authority to get the other's verified public key. It's secure, yeah, but it creates a huge bottleneck. I mean, can you imagine if every single secure connection on the entire internet had to check in with one central office first? It would grind to a halt.
And this is what led to the brilliant system we use today, certificate authorities, or CAs. Instead of a live check-in, a trusted CA uses its own private key to digitally sign a certificate. This certificate acts like a digital passport, and it officially binds an identity, like mybank.com, to one specific public key.
And here's the final piece of the puzzle. Your web browser, whether it's Chrome or Firefox or Safari, comes preloaded with a list of CAs that it trusts implicitly. So when you visit a secure website, that site presents its certificate. Your browser checks the signature. If it was signed by a CA on its trusted list, boom, it accepts the website's public key as authentic. This whole thing is the chain of trust, and it's that invisible handshake that happens every single time you see that little padlock icon in your address bar.
And so we have this incredible, intricate system of trust and security, all built on mathematical problems that we believe are just too hard for today's computers to solve. But that arms race, it isn't over, not by a long shot. On the horizon are quantum computers, and they have the potential to completely shatter the hard problems that both RSA and ECC rely on. Which leaves us with a final fascinating question. What does the cryptography of tomorrow look like? And what will be the next unbreakable lock?